And welcome, folks. First class of Physics 4C here in the spring semester of 26. I hope you all had a winter break that was relaxful and relaxing and peaceful. There we go. But it's over now, so we've got bright sunshine as I'm looking at it out the window here. And if you are near the central coast of California, as we are over here, then hopefully you have some reasonably similar happy weather, because basically if you live anywhere else in this country, the answer is you don't have that. So anyways, we'll move on and get to talking a little bit about what we have in store for the semester. My name is Marcus. I'll be your host. Should questions arise, since this class, of course, is fully online, you can fire me an email either through Canvas or through my email address, which is listed on the syllabus and comprises the first two initials, my first two the first two letters of my first name and then my entire last name. So let's see, we'll start off here and we'll go like this. I'll even write this in small case at Cabrillo. So if you, let's see, how's that showing up? Could be better. So if you would like to get in contact with me, fire me an email. Like I said, the Canvas links directly to whatever you would send me to this address anyway, so I'll get it one way or another. The classes are attendable, as some of you are now, so thanks for being here this morning. They are also viewable on YouTube. I will, after this class, since I'm doing this recording, I will process the video and post it on my YouTube channel and create maybe a playlist for the class videos this semester. I believe I do have ones from last semester up already, so, not last semester, sorry, last year, when I did the Spring 25 class. I think I still have those up as well, so I don't know, maybe I say things differently the second time around and it's double the fun. So if you are looking for the recording, I will post the link to the YouTube channel on the Canvas page, and I will do that basically every class period. So there's going to be a full list every class. There's going to be a YouTube link to make it hopefully easier for you to just track those down. On Fridays is when I publish the, so backing up, the class happens Tuesday, Wednesday, Thursday. The lab happens Friday, and that's at least when I post it. Same kind of occurrence is going on. You don't need to be there live. I think I'm going to start around 9 to 9:30 in the morning doing that, and then I will post the recording of that. It will be up and available probably around noon on Friday. And you are then welcome to go forth and do the lab or wait until the weekend, whatever is going to work, but I do kind of ask that you keep up to date with it. It's easy to get behind in a class like this because of the nature of the disconnect between us, okay? So I encourage you to get things done as on time as possible, all right? So speaking of the lab stuff, the lab and the lab write-ups, I would like them to be finished and completed before we start class the next Tuesday after the Friday that the lab occurred, okay? So lab occurs on the Friday, you got Saturday, Sunday, Monday, and then we start again class on Tuesday. Please have it done by then, okay? The turning in of assignments is going to be all done on Canvas. The first couple of weeks, this week and next week, it's crucial that you submit stuff. If you don't, I will basically consider you not participating, and maybe I'll give you a warning, like there was one missed, you maybe missed one or two things. Hey, by the way, you're missing these assignments. I'll try to keep up to date on that, but ultimately I need you to take responsibility that if you're not going to complete this class, please know in the first week or so, because that way we can get you out of here without a W on the transcript, and then someone from the wait list can come in. All right? So with that being said, I don't think I have too much else that's administrative to talk about, other than the types of assignments that we have. So I mentioned labs. We're going to have a lab activity and a lab write-up. Oh, I do have to mention the lab kits. Lab kits are available here at Cabrillo. So if you are local to Aptos, Santa Cruz area, please come by and pick one up from Julia in the lab rooms. So that would be room 802 here on Cabrillo campus in Aptos. She's generally here Monday through Thursday from about, say, 10 a.m. to 4 p.m. Okay, so see if you can track her down during those periods. If a class is going on in 802, please wait for the instructor to finish actively talking and then ask if you can come in and talk to Julia to grab a lab kit. If you are not local, please send a prepaid shipping label to yourself, right? Addressed to yourself. Send that to Julia. I put her email address on the announcement about it, or to me. That'll work too. But it has to be prepaid and it has to be addressed to you, so that when we get it, we can put it on the lab kit and send it off. All right. So thanks to those of you who've already done that. Good job, and have already picked up their lab kits. Okay. They are due back to us by the end of the semester, so please be prepared to ship it back or return it to us, and no sneakily selling all of the stuff off for the presumably about $10 that you would get for selling it. All right, so there's that. Other assignments that we're going to have in this class include homeworks, of course. Those will be posted. Homework 1 is going to come about sometime today. There are quizzes that are going to go along with the homeworks. There are exams, which I call celebrations of knowledge, which we will have on, thank you, which we will have on specified dates. I specified the week during which the celebrations will be. And then lastly, and this was one that sometimes if you're not familiar with Cabrillo, this is a little bit new. It's called the PLC. It is an outside of class and outside of homework activity. It's actually considered lab time. All right, so every week you will see a PLC assignment pop up. Okay, and the PLC assignment is going to be about an hour. It should be, well, academic hour, 50 minutes. It should be about, be prepared to be spending about 50 minutes on the PLC. I will put them in Canvas as quiz-style formatted things. In other words, there will be a question, probably a couple of multiple choice answers, or a fill in the blank, or a explain your answer, or something like that, and you'll get a couple of chances at doing it. I think I give you 3 chances at going through, getting them all checked off. Sometimes the PLC might take you a little bit more, sometimes it'll take you a little bit less, but on the whole, hopefully we're going to average about this per week. All right, so just letting you know that's there, and is an expectation of the class in addition to all the other things I listed. All right, so this is also part of what goes into making your grade up. All right, other than that, usual thing about keys for success, staying on top of things, contacting me if you have timing issues or questions about problems or conceptual issues or things like that. I do have office hours. I will hold office hours on Zoom. I did say on Tuesdays, which is today, but maybe I'll shift them to Wednesdays. I'm not sure. But I do have Zoom office hours as well as in-person office hours here at Cabrillo. So if you are local, make yourself available for those. All right. Other than that, I don't think I have anything else that's kind of class administrative stuff. The syllabus is there. Please read it and go through it. Obviously, things that are submitted through Canvas, like the exams, the quizzes, these are all, and the homeworks, these are all basically on the honor system. Obviously, AI is getting really good and would probably do quite well, but I have to trust you not to use that and at least turn in your own work, okay, every single time. Question.
Yes, will we be having to turn in our lab notebooks at the end of the semester?
Not as a whole, but you'll turn them in weekly. So when you do the experiment, write it up and then send it off, and then you're done with that chunk. You'll just do that every week.
Okay. Thank you very much.
Sure. Thanks for the question. Other than that, like I said, yes, please do be on the honor system, and I will trust you as much as I can. And I will go ahead and consider giving you the warning now, so that if I have to have the talk with you about honesty and not either plagiarizing or collaborating or anything like that, this is your first and only warning on that. All right. So if there's going to be an instance of that, it's going to end up immediately going to. I'm going to ask you to leave the class. I'm going to report to the office of whatever that takes care of all that stuff. All right. So this is your first and only warning for that. Any violations of that immediately go straight to consequences. All righty. Question of whether there's any in-person. No, as I said, this is an online class and everything's going to be done through Canvas. Alrighty, so let's go ahead and get started with some of the material that we've got going today. In terms of ordering of events, what we have is starting out. We're gonna start off with geometric optics. We're gonna start in general with optics. So we have three basic models of light. We're going to start with the ray model. We're going to move to the wave model, and lastly, going to hit the photon model as part of our unit on optics. We're then going to move to heat and thermodynamics. In the past, I have typically started with this, and this semester I'm choosing to change it up a little bit. And lastly, we will be talking about modern physics, which is physics since about 1900, I guess, which is the developments in physics since about 1900. That includes, and we will spend time on special relativity, which was Einstein's idea in 1905. We will spend some time on the basics of quantum mechanics, which started around 1915, 1920. So that's modern, okay? So those are the three kind of large topic areas that we're going to hit this semester, and we're going to have a celebration after each one, all right? So I'm assuming that we're going to get about 6 weeks or so for 5 to 6 weeks for optics, 5 to 6 weeks for thermo, 4 to 5 weeks for modern. It'll be somewhere around in that fraction. Alrighty, so we're going to start with ray optics, and your lab this week, when it posts on Friday, will deal with ray optics. Now, one other thing I want to throw out there is that these recordings, I went back and I viewed some of my recordings from last year, and in some cases the video was not, I mean, the quality varied. The audio quality was sometimes very up and down. So if there are problems, I'm probably not going to know about it right away. So if you have feedback on, hey, the audio was really muted, or I couldn't hardly hear you, or I'm having difficulty reading what you're writing on the board, please send me that feedback so that I can try and make an adjustment and make it ultimately, right? This is supposed to be something that I'm doing for you. So if you're not happy, please don't let me know that you're not happy, but please give me an idea that I need to adjust something. Let's go about with that. Okay, so I'm currently refilling my pens, so perhaps the ink will show up a little bit better. And we're going to roll. So ray optics involves the essentially straight line travel of rays, of light rays, all right, straight line travel of light rays, and I got a bit of glare right there that I will avoid, and that occurs when the light is traveling in a homogeneous medium. I guess I lied. I'm going to put medium under here. In other words, as long as the light is in the same thing, so if you examine the air in the wherever you are, there's a packet of air that's right here, and there's a packet of air that's right here, and if I measure some of the qualities of the air, right, its density and temperature and pressure and all this type of stuff, and I compare it to over here, and I say, oh, these are about the same, I would expect light to travel in a straight line in this medium. Now, when it then changes medium, it changes its media, right? Then it's no longer homogeneous, it's gone into something else. So after it gets into that material, if that's a homogeneous material, then it'll have, again, straight line travel. However, transitioning from one to the other will cause a change in the direction, and we will explore that probably next week when we start talking about the refraction of light. But the idea here is that when light travels, for us as we are considering it to be a ray, it's going to be in a straight line path. So for our first exploration here with reflection, I have the laser beam here. Oh, good. Can you see it? Kind of. Okay. So here I have the laser beam, and what I can do is I can line it up with my board, and I can kind of, it fades pretty quickly. I can kind of show you that if I just move it along here, you would imagine that the light's leaving the pen, the diode here, and going straight to where it hits the board, right? So as I move it this way, it now arrives over here. When I move it that way, it arrives over here. So it's easy enough to imagine that there's a straight line laser path, and if you have ever seen a laser light shining in fog or in something that it could scatter off, then you'd see that there's, yeah, indeed, there's a straight line path of the laser through the material. So we'll start with that as kind of a overall mentality about what the ray model is trying to get to, and then we're going to move into reflection, and we're going to talk about the law of reflection. Which means that we're going to think about what happens when the light ray hits a material which is different from the one it was in. Excuse me. Now, if you think back to something pretty basic, and this is what one of the things I really enjoy about physics, is that even if you're considering a question like, how am I seeing? You have a couple of different ways of attacking the answer to that problem, because it has many facets to it, right? How am I seeing might involve what's going on in my eye in order to cause the light signal that entered it to be transmitted into electrical signals that get decoded in my optic nerve and brain. Okay, well, that's not really what we're going with, but what I want to talk about is, let's think about the light that is getting to your eye, and maybe a little bit later in the class we'll talk about what happens after it gets into your eye and what's going on with that. But for now, let's think about, why do we see stuff? Okay, why do we look at things? Now, of course, I turn the lights on and I can see the lights. Okay, that is pretty straightforward. these are emitting light. Okay, great. What about everything else? Like, this is not emitting light, so how do we see this? Okay, well, now you're thinking about, okay, the light that is emitted from this light fixture is hitting this pen and basically getting scattered in every single direction, because there's no point that I can stand and not see the pen. Okay, there's nowhere I can stand and not be able to see. Oh, it just went dark for a second. I couldn't see it. No, it's everywhere. So the light rays that are hitting this pen are hitting, for example, say the top of the cap here, the cap up here, and that light is getting scattered in literally every direction, because there's nowhere that I can stand that I wouldn't be able to see it. Okay. So thinking of reflection, there are well, let's talk about a simpler case, right? And the same thing, by the way, is happening here on the board, right? The light rays are hitting the board and scattering in every direction, and one of those directions is straight into the camera, so that you'd be able to see this. Sadly, I guess it's also kind of, what's that? If you can just block that off, that'd be even better. Oh well. So let's take a simpler example of reflection, and let's look at a mirror. Let's suppose here that I have a mirrored surface, okay? And I have light that's coming down. I'm shining, for example, my laser beam onto the mirror here. And the question you might ask is, well, if it reflects off here, where does it go? And there are a number of possibilities, right? I mean, it could go this way or this way or this way. It could bounce straight back the one it came. What we find, however, is that if we measure the angle that this light ray makes, not quite with the mirror surface, but related to the mirror surface, then what we find here is that it bounces off at exactly that same angle. Now, for reasons that we're not going to be able to explain now, but will help because we are going to do this later, the angle that we want to measure these rays with respect to is going to be this angle here that is to the normal. Now you might think, why would you do that? Why not just measure this angle down here, because that's the angle from the mirror to the incident ray, and that's easy enough? Well, that would totally work. There's nothing whatsoever wrong with doing that. It's just that in the next piece, we're going to measure to the normal. So I'm just getting you started. Just measure to the normal all the time, and then you never have to worry about it. Because then you have to think about, well, am I measuring this one or am I measuring this one? And it's a really easy thing to stumble on, all right? We always measure light ray angles with respect to the normal, okay? Alrighty, so measure with respect to the normal. And what we find is that the reflected angle, in other words, the angle that is the angle to the reflected beam from the normal, is exactly the same as the incident angle, like so. I'm going to say it's about, maybe it looks about like that. All right, so this here is our incident angle. And this here is the reflected angle. And the law of reflection is that those two angles are equal. In other words, if you think of it as a predictive sense, I'm wondering what's going to be the reflected angle. The law is that the reflected angle equals the incident angle. fairly straightforward, hopefully, and probably something that you will have all relatively well observed. Okay, so going back to the question of how do we see stuff. All right, now if I were to say put a detector, or if I'm considering this a laser beam, then I'm going to try and practice safety and not put my eye in the way of it. So I'm going to try and find the laser beam with my laser beam detector, my light detector. I'm going to put the light detector, say, down here, right? And it's going to say, all right, is there any light coming in? And it's going to say, no, there's no light coming in. Why? Because the beam missed it. So if this was your eye, you wouldn't see the laser beam because it's not going into your eye. The reason you see things is because light enters your eye. If you think about light that's not entering your eye, well, then you're not seeing that light. Okay, now there's plenty of light that you're not seeing because it turns out that your eyes only have a really small opening in them. Okay, so any light that doesn't go straight into there is not seen. It's not processed by our eyes. Okay, now if you shine a laser beam onto a mirror, onto a plane mirror like this, right, a flat plane mirror, what you will likely see if you are doing it such that the beam is, say, suppose I have a mirror which is flat like this, and I'm shining the laser beam in and it's going straight out like this, right, straight in and straight out, because ultimately if I shined it straight in, it would just go straight out because the angles would be zero. Yeah. So what I've told you is not quite true because, well, I should say the law is true, but when I say that you wouldn't detect any light, that's not quite true. Because if you look at the mirror, right, the laser beam is hitting the mirror and then bouncing straight back. But if I'm looking at the mirror, right where the laser beam is hitting the mirror, I can see where the laser beam hits the mirror. Because when it hits the mirror, there are some parts of it that are not 100% specularly reflected. This, incidentally, is known as specular reflection, when the angles are equal. So that is not a violation of the law of reflection, because ultimately this is a law. And in physics, we like laws, because that describes the behavior that we've observed. Okay? And that means we've discerned this pattern. Okay? So you would say, well, if I'm thinking about the light that's coming, the light rays that are coming away from the lamps up here, I guess I have to stop calling them lights. The fixtures, the light, right? They're coming down like this. Now, how are you seeing them then, right? Because the light, if we kind of backtrack, the light that's entering the camera is going this way, right? But there's no lights over there. The lights are up here. So how are the lights hitting this and then coming out? That seems to be a violation of the law of reflection, yeah? Because the light from the lamps up in the ceiling is coming down like this, and it would be about like that, hitting, but then coming out like this, whereas you'd expect that they would be going more like this, right? So the question here is, what's going on to make the light do that? Okay, and that means that we're going to have to examine the structure of the material upon which the light is incident. Okay, now what I've drawn here is an atomically flat surface. Okay, and you think about the size of light. Well, it basically doesn't have much size, right? So when it hits a surface, if that surface is not flat on the order of about how big the light is, well then it's like it's hitting mountains and valleys and peaks and stuff like that. Okay, so we'll give this picture here where I have a nice flat surface. We'll call this the specular case. This is specular reflection. Okay. Oh, here we go. And now, what we might do is we might ask ourselves, okay, what happens when the material that the light is landing on is not quite so flat? Now, for us, we have a very crude sense of touch, and you'd say, oh, well, I can feel this whiteboard. It feels pretty smooth. Yeah, but we're not light, right? Our fingers and our senses on our fingers are not as small. They're not going to tune into the slight differences that light's going to tune into. Okay, so imagine that we are a beam of light. What do surfaces look like to us? Well, they're made of atoms. They have a lot of topography to them, right? There's lots of ups and downs and bumps and this and that, right? So you'd look at a surface like that, and I mean, I'll exaggerate, but it might look pretty craggy, right? It might look kind of like a mountain range. Now, if light is shining in on this, notice what's going to happen. Remember, we're measuring the angles to the normal. So when I think about the normal to this surface, is that normal changing? Is the direction of that normal the same, or is it changing? Right? Well, examine a situation like this, where I have this piece right here, which is relatively flat. So if I drew a normal to this, it might be there. Okay? Whereas if I look at the next piece over here, well, this piece over here, it's kind of inclined that way. So if I did a normal, it would look a bit more like this. Okay? If you can kind of see those well enough, yeah. Right? And likewise back here where it kind of curves around like that, if I think about this piece right here, well, that normal is going to be something like this. Right? It's gonna be a very different direction for the normal to the surface. If I now think about shining light onto this surface, and maybe we'll talk about that in a minute, but if I think about shining light onto this surface, suppose I have a beam of light, and it's got a fairly, if you think about a laser beam, it has a certain size to it, right? It might be about the size of maybe a pencil, right? Or so, the laser beam, maybe a little less than that, maybe a bit thinner, but the point is it's not a single ray. We don't ever have a single ray like I drew here. Every ray is a bundle, right? So if I think about the ray of light that comes in to here, then I'm going to say, well, that's easy enough. It's going to bounce off that way, okay? Because it obeys the law of reflection, as it must. The angle of the incident ray, right, which is on this side, should equal the angle of the reflected ray, which is over on this side. Okay, now I'm going to say, all right, suppose I take a parallel incoming incident light ray and it hits somewhere else on the surface. Okay, now if I think about that coming in here, it's going to go like this, so that's going to be here. And about, is that reasonably parallel? Close enough for government work, right? But now look at the size of this angle that it makes. This angle is really big, so I got to go all the way like that, right? This thing's not going to come out until like going that way. And it's going to hit right into that thing. Okay, so you can see, right? And if I do the same thing here, right, coming in like this, hitting this one here, it's going to bounce basically almost straight back. That incident ray is basically almost coming in straight on the normal. So this is the situation that we most commonly occur, we most commonly perceive, okay? And that is that light hits an object, and like we kind of tried to reason out in the first case, I can see the cap of the pen from any angle. Why? Because when light hits it, it gets shot out in every direction. Why? Because the cap, though it might feel smooth to my finger, is not a smooth to light surface. This is known as diffuse reflection. In other words, the light is getting diffused outwards as if it's just getting scattered out in every direction. However, it is still, I hope hope I'm able to convince you, it is still subject to the law of reflection. It is still doing the same angle out equals angle in procedure for every beam, even though the light's going on, the light is leaving in vastly different directions. The reason is because the surface is in vastly different directions. Okay, and so this is relatively akin to maybe like rock skipping on the lake or something like that. Well, maybe not. That wouldn't really work because you wouldn't have it coming off at some weird angle. Never mind that. But the idea is here that even though I have parallel incoming rays, I have not parallel outgoing rays. Whereas were I to add another one here, I would find another one going along here, right? Anything that's parallel with the incident ray here would simply be reflected as a parallel with the reflected ray here. Okay. All right, so the reason that we see objects that are not actively emitting light, objects reflect light, and they do so diffusely because their surface is rough on the scale of a light beam. All right, so we start with that, and we can move into some topics about mirrors. Okay. Now, okay. So let's do this. Alrighty. Well, let's look at a plane mirror once again. And I want to introduce you to the idea of drawing the rays in order to try and predict what the ultimate outcome is going to be. And when I say outcome, what I mean is when you look in a mirror, you are expecting to see an image, right? So our outcome is, where is the image? What size is the image? Is the image upside down or right side up, right? We're trying to answer those types of questions. So let's look at images created by reflection. And I want to introduce you to the main pictorial way of doing this. Before I do that, I want to take a quick interlude here to let you know about some of my philosophical tendencies here in physics. Now, for me, what I want to really emphasize, and this is going to be, you'll find this throughout the semester, throughout all of the topics we talk about, I'm going to introduce pictures first and ways to visually represent the phenomena that we are going to discuss, okay? I expect that you will learn these pictorial methods, and these are the things that I am interested in essentially having you learn. Because once you learn how the picture works, you can kind of you can either apply math and figure something out, you're right, you can apply math to the picture, or you can actually use the picture itself to derive what mathematics you need in order to solve a problem, all right? So I am encouraging you always, throughout the entire semester, you'll find this is going to be a repeated statement. I encourage you to draw the pictures. Start every problem as best you can by drawing a picture for it. That's really what I'm looking for, and that's how I want you to start most of the problems that we're going to work on. And I won't say every single one because sometimes sometimes it doesn't quite work out, but for the most part, what I do here for you in terms of drawing and hopefully introducing you to how to represent these situations pictorially, you will take that and really learn it as best you can. Okay? So for me, if you were here and wanting to plug numbers into equations, and that's not really how I do things, okay? So I really want to encourage physical thinking and physical reasoning over plugging in numbers to get a number answer, okay? I'm almost completely opposite just plugging numbers into equations, okay? I really want to think about what the physics is that's going on. And so one of the ways we do that is by drawing diagrams. So let me introduce you to the ray diagrams. We're going to draw the rays that emanate from an object, which then hit a mirror and for us then cast an image. Okay, so we are interested in trying to find out where is the image, what orientation is it? Is it upside down? Is it right side up? Where is it big? Is it small? Where is it, right? So we're trying to predict this, and we're going to use the ray diagram to try and figure out what's happening. Okay? So, if I think about a plane mirror, we'll start with that. This is the simpler case. Okay, we're going to have a plane mirror here, like so. And when I do this, in most cases, my silvered side of the mirror will be the left side, such that the light is all over here and is bouncing off the mirror and coming back this way. Okay, generally that's how I draw mirrors. Okay, so that means I have an object over here and I'm interested in figuring out what image does that object create in the mirror. So let's suppose I have, let's suppose that I have a candle sitting here. This is a relatively small mirror, so we're going to want some kind of large candle here. Okay, let's just knock that to there so it's on the same, okay, like so. Maybe that mirror is sitting on a table or something, the candle's sitting on a table, so we got them at the same level. That's neither here nor there for this. Kind of back to the question about why do we see things? We see things because light is either emitted by the object because it's in the process of being a light or a lamp or a light bulb or something like that, a source of light, or it's reflecting light, as we've already seen with this picture over here. This is a candle, so it's actively emitting light. The candlestick here is actively reflecting light, okay? Now, why ultimately do we see the candle? Okay, think about, if I just think about, say, the tip of the candle, the flame up here, way on the top of the flame. Why am I seeing that? And one reason is that one reason is because we have two eyes. We can locate things in space, right? We have good depth perception because we have stereoscopic vision. Nonetheless, even if we had one eye, it would still, it's not quite so good with depth perception, but I would still be able to see the object, okay? Why do I see the object? I see the object if I can just draw a little, I'm going to draw a little something, so some light going this way just in order to illustrate this. Okay, so if I see an object, my eye, which is up here, there's a light ray which goes from the top of the candle directly into my eye. So I go, oh, there's light here. Okay. Now, what else do I want in order to be able to see something? I need for that light to be diverging a little bit. Right? So in order to get a good spatial location of where the light is, I've drawn these fairly close together, but the idea is that they are like this, right? I drew them at a shorter angle than that, but these light rays are diverging. Okay, just as we talked about with the pen cap, when light comes in and hits and gets scattered off in all directions, that light diverges. That's why it's called diffuse reflection. It's creating diverging light rays which are going in every direction from the object. Okay, now that's going to be true here. The light rays come from a point and go outwards. That way we can say, the object is right there. It's almost like a basic triangulation problem, right? So what happens is these two light rays are entering our eye by going like this, right? They're entering our eye. I guess I have a large eye, right? And our brain is going, where does it look like they came from? Right there, where they meet. So our brain is kind of backtracking, right? It's assuming that light has traveled in a straight line, and it's going, it came from right there. Okay? When we see something, that's basically what we're doing with these light rays. We're saying, these light rays were diverging. They came from right here. Therefore, whenever we're looking for an image, we're looking for diverging light rays. Where does it look like they came from? Okay? Back to the mirror then. Okay? Now, if we've got that working as kind of a mentality, all right, so these are diverging light rays. Okay, and in some sense that describes the spatial location of the place where they came from. Okay, so if I think about doing that, but going this way towards the mirror and thinking about what's going to happen when the mirror then reflects that light. All right, so here's what I'm going to do. We're going to do, let's try this one here. I don't have a straight edge with me, so this will be close enough for government work. Suppose that I think about a light ray which is coming off the top of the flame here and going that way. Okay, I can use the law of reflection on this light ray to try and figure out where its reflected ray would be. And if I do that, I'm going to say, well, my normal is about here. Okay, so my light ray is going to be about there, and I'm going to try and draw it in like so. It's going to be about like that, say? Something about like that. If I'm looking in, okay, see, I know that I can see the candle, right? That's fine. But now I want to orient my eye so that I'm looking at the reflected rays. Here's one reflected ray. I need another one, because ultimately what I want to do is this exact procedure right here, where my light rays came from a point, right? And obviously we're doing this in 2 dimensions rather than 3, so I just keep it simple. Right, I need 2 light rays to find where do they intersect. That's my point. Okay, so right there, that's how I discern where that point is in space, is because my brain traces back the paths of these rays. I need one more, because I've only got the one light ray here. I need one more to try and figure out where does it look like they came from. So let's do another one. I'm gonna, for drawing purposes, you'll have to imagine perhaps my eye is kind of large or something like that. But for drawing purposes, I'm going to draw it down here rather than trying to stuff it in up here so you can see it a little better. I'm going to draw one to, say, here. Where was I going? Let's go to there. All right. Okay, so here's another light ray that's leaving the top of the flame. Okay, I'm going to apply the law of reflection once again. Here is my normal. Okay, and so I'm going to say, all right, so that's there and that's about there here. So let's say it's more like there, and then here. So I'm looking to go down like that. The reflected beam is coming down like that somehow. Okay, never mind that it basically makes no sense, but the idea is that we visually now have 2 reflected rays. Okay, I have 2 reflected rays, these ones right here. Therefore, when I see these, okay, suppose that they now enter my eye. I understand the scale is not good, but work with me. All right, so now I'm looking at these 2 rays. They're entering my eye. They are definitely diverging. right? This one's definitely leaving down here. This one's definitely kind of moving up top here, okay? What does my brain do? My brain says, hey, pretty cool. This looks like they came from a point, but there's no way they came from a point because there's nothing over here. So how did they come from a point? Well, the answer is they didn't. It just looks like they did. So what I'm going to do now is I'm going to do what my brain tells me I am supposed to do, which is I'm going to try and find the point where it looks like they came from. And that's going to determine my image point. Okay? So I'm going to take this thing here, and I'm going to go, let's see, backwards. This is where I really want my straight edge. Where do I get? Do I have something I can use as a straight edge here? Okay, I can use this. All right, so I'll try and get this somewhat without freehanding it too badly. Okay, it's going like that angle, so I'm going to go like this angle here. How about like that? It's going about like this. We'll say about like this. Somewhere like that. Alright, so let's keep going. This is a poor large ruler, but I think I got a reasonable, looks like a reasonable continuation of that line. Now I'm just going to do the same thing with this one to see where does it look like they came from. Where these intersect is then where my eye is telling me that's where it looks like the top of the flame is. Okay? So now I'm going to take this one here. Ooh, this one was a little bit curvy, huh? So let's go with that piece to there. We'll go backwards from here. Okay, it looks like right there. Looks like right about there is where they intersect. Therefore, if I were now, since I can orient the rest of the reflected rays, if I were to then draw some reflected rays, or some incident and reflected rays from the base of the flame, I would find that it would reproduce down here, right, straight across. And if I looked at where the candlestick was, well, then it would be down here. So I found the very top of my flame, and if I pick any other point here, I'm going to find that it's below. So my image is basically looking like this, down to here, like so. All right, so this would be my image. And we refer to the candle in this case as the object. Okay. Well, let's see here. How did we do? Missed by a little bit. What we find is that it seems just by, I don't know, careful inspection, I'm not sure if that's quite the right word, but just realizing that this diagram was not drawn with the greatest of precision. Nonetheless, it appears as though the image is the same height as the object. Just kind of looking at, I got them on about a level here, right? The top of that one is about where the top of that one is. So it seems as though the height is the same. And I think you would probably concur with that if you have ever looked in a mirror, like a plain mirror, like a bathroom mirror, right? If you ever looked in a mirror, you'd say, yeah, my head is that size, my eyes are that size, right? It's not distorting. It's not one of the funhouse mirrors. It's giving you a fairly faithful reproduction of the size of you. Okay? So it looks like we've got that reasonably knocked out. We'll say, I'll just keep track of this down here. Image height. seems to be approximately the same as object height. Now, this is exactly what a ray diagram is for. You should not take extreme care to make them precise and scaled. You should take care to try and figure out what is a result of imperfections in the diagram and what is a result of physics. Okay? Now, that looks like okay, those seem to be about the same height, and it kind of tracks with what my my common sense is about the plane mirrors. Next question, what about the distance the image is behind the mirror? Now, if you're looking carefully, you're going to notice they're not the same. This one here does not look quite the same. So I counted them up a little while ago. I'm off by about 1 grid square. I don't know if you can see the grid squares on my board here, but yeah, you kind of can. I'm off by about 1 grid square here. Now, is that going to be something in which I'm going to ascribe extreme meaning? Or should I wonder, wait a sec, how good was my diagram really? Okay. For example, you can kind of see this line here doesn't quite go with that slope right there. Maybe you can kind of see this dashed line slope is a little bit more than the slope of the ray that I drew here. Maybe it should have gone out a little bit. Okay, so I didn't pay close enough attention to get that exactly right. So what I'm going to say is it looks like they're about the same. In other words, this image is not way up next to the mirror, and it's not way back here. It's kind of in the neighborhood of being close to it. And what would you expect? If you think about your experience with the plane mirror, you'd expect, yeah, it looks like you're about the same distance away as the image is in the mirror, right? The image does not occur on the mirror. The image occurs behind the mirror, all right? So in this case, the image distance is approximately the same as the object distance. So in answering these questions, and let's see, how does that look? Can you read that? Maybe. I got to squint out a little bit. I'll try and write a little bigger. In answering these questions, we are answering fundamental questions that we would have about, well, what kind of image should I expect, right? I want to know, well, where is it? Okay, if you want to know where it is, all you got to do is measure your distance in front, and it'll be that distance behind, approximately. Oh, how big is it? Oh, just measure your height, and then that'll be about the height of that. Oh, okay, great. So these are the questions that we have about what type of image is formed, okay? Another thing we can notice about this is that the flame is on the same side. In other words, it's not flipped over, it's an upright image, okay? And when I say upright, I mean compared to the object. This is going to sound weird, but if I took the candle and I flipped it over, and let's suppose that it was somehow still burning, maybe freeze everything, freeze the flame and turn it over so that it's like we're in a Marvel universe and I've got the frozen flickering candle here and it's upside down. I look at the image in the mirror. The image in the mirror, of course, is going to be this way. It's upright. Why? Because it has the same orientation as the object. When we use upright or inverted to describe an image in this sense, we're talking about what is it upright or inverted compared to that. In other words, I don't put the candle here and see this, right? I see this. That's upright. Whether I do this and this, that's still upright. Okay? So it doesn't literally mean that it's upside down. It means compared to what we had as the object. All right? So we've got these three things pointed out. Now, I want to put one more thing in here, and then I want to set these as a consistent set of questions that we want to answer about every image. In this case, I had to trace the rays in order to find a common, say, emanating point. Okay, in order to find the point from which it appeared to someone standing on this side of the mirror that they came from. So when you look in the mirror, it appears that there's an image of the candle back here, because that's what the light rays are doing. They're bouncing off the mirror and they're coming out like this, and your brain's going, where did it look like it came from? Right there. When I have to trace these back to find the common, I don't know what, the common emanating point, the common, where they cross, right? For lack of a better terminology here. If I have to trace those back, we have a name for that. Okay? It's going to sound a little weird. But it's known as a virtual image. Okay? Because light did not actually start here and travel out. Right? There was no light in this region right here. There's no light that's making this image at this location. So for the purposes of mirrors and next week when we talk about lenses, it will be the same type of idea. For this purpose, we know that nothing is going on here. It's all going on over here. So we call this a virtual image. Okay? So in this case, when we say that is a hallmark of what we call the virtual image. If I have to trace the light rays back, say behind the mirror, typically, right? Because no light's back there. This is a mirror, right? All the light that we're interested in is on this side of the mirror. There's no light that we can see that's back behind the mirror. So if I have to trace the light ray paths back in order to find where their points of, say, convergence, which is the word I used here, if I have to find that point of convergence, then we know, then we term that the image is virtual. And if you like to think of it, then what we can do is kind of divide the space. And we can say this is virtual space back here, whereas this is real over here. Now, these terms date back to well before virtual reality, which is virtual and real, all right? It has no other meaning other than, in this case, the image is behind the mirror, where there's no light that we're seeing. All right? It doesn't carry anything more than that. When I talk about real, this is really happening, this is where light is. This is, I mean, sure, it's also kind of happening, but it didn't in some sense, because this is not a light ray, and that's not a light ray. Okay? They're just kind of there because we thought that they looked like that they should be there. Okay? These here then form a set of 4 questions. These are the 4 questions. If you've ever answered 4 questions, well, maybe they were different from these. But these are our 4 image questions. We want to answer these questions every time we sketch a ray diagram and try to determine what properties an image has when we find an object in front of a mirror. And consequently also next week when we talk about lenses. Okay, so this is a set of 4 image questions. just easier to think of them as the 4 questions. You might ask yourself the 4 questions. Is the image real or virtual? Right? Do I have to trace the ray back? Right? Then if I do, it is virtual. If I do not, it is real. Is the image upright compared to the object or inverted? Is it the same height as the object? Is it larger than the object? Is it smaller than the object? Right? We address the height image. Where is the object? And at what location should we be looking to find the image? I said object, sorry. At what location should we be looking to find the image? What's the position of the image? Okay? So in this case, we'd say the image is behind the mirror, and it's about the same distance behind the mirror as this is in front of the mirror. Right? That's how we position. Okay, that's where it is. That's how high it is. It's upright, and we term it virtual because we had to trace these rays back. So those are the 4 questions. Okay? Every ray diagram we have to make, we have these questions in mind. Okay? All right. Is there anything else I want to say about this? Not so much, other than this idea can help you play much better billiards, right? If you have one of those trick shots where you have to bump if you have to hit a ball off a cushion in order to hit another ball and get it to go into the pocket, or even just go around something and have this ball go into the pocket, whatever it is, you're basically using the law of reflection. Okay? Now, a billiard ball is not quite as good at reflecting as light is, but nonetheless, if you consider that I want to hit a ball to a point on a cushion and then have it bounce off and go into a pocket, just imagine where's that pocket. That pocket, right, is right along this line. Right? It's as if when you think about I have to have the ball go this way. Oh well, actually I guess I'm not quite saying it right. If I have to have the ball, let's do it this way. If I have to have the ball go this way, hit, and then go into a pocket this way, then all I have to do is aim as if the pocket is over there. Right? So it's really helpful when you're playing billiards to imagine another table right next to the table you're playing on, and you're going, okay, where's that pocket? It's right over there. All I got to do is aim the cushion right at that pocket, and it's going to hit and go into this one. So there you go. I probably just made you hundreds of thousands of dollars. I mean, what? There you go. You could practically be a professional billiards player at this point, and you're going to be rich, famous, and it's all due, I mean, I would say it's me, but really it's the law of reflection. So you're welcome. That's from me to you. Let's take a look at some other mirrors, ones in which the curvature is more prominent. Okay, this was the situation here with a plane mirror. What's going to happen if we look at a mirror in which there is significant curvature? Okay, so for demonstration purposes here, I'm going to go ahead and erase some of this. Okay, so here I have a strip of plane mirror. You can kind of see, right? This is what it looks like. So if I shine my laser beam onto this thing, I'm going to try and hold it like this, and let's see if I can get, so here's my laser beam. I'm going to shine it on the board, and I'm going to have it go like this, and you see where it hits. Let me go down a little further down here. So you see where it hits the mirror. Whoops, right there. Right? You can kind of see the law of reflection happening right there. That angle to there and that angle up there. Pretty close to being the same angle. I'm also wiggling the laser around a little bit, so there's a little bit of uncertainty involved there, but nonetheless, okay, there's your law of reflection. And it does that the same way no matter, and I'm also tilting this thing back and forth, it does that the same way no matter where I am on the mirror. Right? If I'm down here, it's doing it the same way. Okay? here's a curved mirror. We're going to start off with the curved silver piece out on this side, okay, like so. Now, if I look at it, it's a little bit different. So now I'm going to shine in straight. Whoops. Well, I'm going to shine it in straight. Where is my laser beam? There it is right there. So now, can you see? You can't really see where it's going. You can barely see it. Wonder why that is. It was way easier to see it on the other one. Okay. So here, I'm shining the light in straight. Oh, there you go. You can kind of see it. Boop. Up right there. So if I'm shining the light in straight, in other words, horizontally, yeah, I'm trying to make it horizontal, and you see the light beam is not coming out horizontally. It's going, where's it going? It's going way up there. You can't see that too well. What if I move back this way, get away from some of that glare? No, I'm not seeing it at all. Well, barely right there. You can see it hitting my arm right there. Ow! The pain I'm enduring for you people is excruciating right now. Just have laser beams boring through my arm. Okay, so what this is telling you is that even though the light is coming in horizontally, it's not bouncing straight back horizontally due to the normal of the surface. The normal of the surface is like this, right? So the light's coming in and then bouncing off and going like this. Yeah, well, for some, I don't know why this is not working as well as the plane mirror. Here's the other side to that mirror. Let's do this. Here's the other side to this mirror. If I do this, there it is there. Boy, you can't see it. That's so weird. Not that this is supposed to be a class or anything, but why is that happening? That's really easy to see. But that is not. Okay, well, Zoom is screwing it up again. All right, I'm gonna draw this one, and then I guess we'll pick it up. We'll pick it up tomorrow. So let's examine. This is what I'm going to call the converging mirror. Again, assuming the silvered side to be on the left, so that that's where all the light is. I'm going to do the same thing. I'm going to put a candle there. Now, though, in this case, I'm going to be a little careful. Here, I just said, oh, willy-nilly, I've got a plane mirror, I've got a candle in front of it. I'm going to be a little more careful about where I'm putting the candle in this case, because I'm going to denote that there's an axis of symmetry for this mirror here. And it looks like it might be just about there. In other words, if I folded the bottom onto the top, it would match right here. So this is my axis of symmetry. It's called the optic axis. When we do curved mirrors and next week lenses, this axis is quite meaningful. So it's useful to set the object on that axis in order to bring out its image characteristics. All right. So I'm going to set the candle right here, and there it is. Now I'm going to look and say, okay, if I think about a ray of light coming off the top of the candle, just like I did with the other one, I can use the law of reflection on my curved mirror. That is going to involve drawing the normal, and that normal, we know, is going to change direction. So if I bring this thing along here, here's an incoming light ray. Now, obviously, I may have said this before, the candle emits an infinity of rays. Okay, it takes me too long. I don't want to waste your time drawing all of those rays. But take my word for it, it's a lot to draw an infinity of rays. So I'm just going to pick one or two right now, and we'll just go with that. Here's this one. The question is, where does it go after it hits the mirror? Well, I have to go through and say, okay, well, the tangent to that looks like it's kind of like there. And so if I constructed a normal, it looks like it might be going there. And if I say, okay, well, that means it's going that much and that much, I'm going to expect it to then come back down through here. It's going to go that way. my reflected ray is still obeying the law of reflection. But remember, it's because the normal is changing direction. Okay, so my incident ray and my reflected ray have the same angle. I'll make the normal a little bit bigger so you can see it. Okay, I was thinking it lies along, kind of about along here, right through there. That's where I was thinking the normal looks, so that the angles are about the same. Okay. Now, what I'm going to do is I'm going to choose myself a simple one, and I'm going to say, what if I just hit right here? The tangent to that would be vertical, which means that the axis here is basically the normal at that point. So any incident ray that comes into this point then leaves at the exact same angle and goes out that way. So I'm just going to pick the easy one here and have it go there. Whoops, a little bit curvy on that one. All right, so here comes my second ray in there. All right, I'm going to have it go out like this. Oh, it's kind of curving down a little bit, I think, but nonetheless, look what happens. I reach a convergence. Yeah, can you see that? Those two light rays, that one's coming in a little bit steeper, this one's coming a little bit more shallow. They cross right here. Okay? They cross right there. What that means then is that if I'm looking at the image, right, my eye is here, I see diverging light rays coming off from this point right here. Okay? I see the diverging light rays. The diverging light rays are going going like this. My eye doesn't have to work very hard. It goes, yeah, they came from right there. Right? So they are diverging away from this point. Therefore, that's where the image appears to be. And that's the tip of the flame. So now, since we know that the bottom of the candle was there, the bottom of the candle is now here in the image, and the image looks like this. That's object up here. Okay? So now, considering the 4 image questions, we have some slightly different answers, right? This image, well, let's start with the first one. This image is real. This image is actually getting formed by the convergence of light at that point. Not like this one. This is virtual. I had to trace these back. These are not light rays. Those are. That's the path of the light. So that's making the image. It is crossing there. That's a real image. Okay? That is a real image. You can see that it is inverted compared to the object. That's one of the first things that stands out to you, right? It's not the same orientation as the object. It is slightly closer to the mirror than the object is. Okay? Closer to the mirror. Slightly less, so the image distance is less than the object distance, we would say in this case. And furthermore, it is on the same side of the mirror as the object is. That's important because that one wasn't, right? This was not on the same side as the object. That's on the opposite side. By my eye, this looks magnified. Looks like a bigger image. Sometimes that can be hard to discern from a ray diagram. Okay. All right. So, summary for today's class: draw ray diagrams. We're just starting, right? But I want to get you thinking about the paths of the light rays and how we draw those. What does it mean for the image then? Okay, this is one way to consider that. Okay, use the image that you found. Excuse me. Use the images that you find from your ray diagrams to answer the 4 image questions. Now, you may not always be 100% correct, especially when it comes to is the image magnified or minified? You may not always be correct with the ray diagram. However, this is an easy way. We will eventually do some calculations to check whether or not these are all what we're expecting. Okay? But right now we're starting off with diagrams and drawings and thinking about rays, and that's what I want to get you started on. So on the homework, you'll find that there's going to be some, hey, draw the ray diagrams. I'm kind of going to put it out there that that's what I'm expecting you to do first, and then go into doing calculations later. Alrighty? So for now, we will call that good for today. We'll pick up here tomorrow. We have today, we have tomorrow, we have Thursday, so we'll have 3 days on talking about reflection, and then we'll hit the lab on Friday. Alrighty? So I say happy day to the rest of you, and enjoy the rest of your day. I will see you all tomorrow. Hopefully we'll still have good sunny weather out tomorrow, but hey, I guess that's what we pay for. All right? Ciao for now, folks.